last year. And what you've got is a little MATLAB icon. I like coding in this, but lots of other languages are available. And today we'll mix it up. We'll do some Python, we'll do some MATLAB, we'll do some Excel and generic stuff. So that little icon there, you can download all the code for today. And if you want to have a look at the challenge for last year, you can click on that 2022 icon. And anything that looks like a YouTube button is. So you can get some video if you want to have more of me and this idea, in the future. Okay, so I'm just going to go and minimize that. Okay, so there we go. We're going to talk about today probably one of the big stories of the last 5 years, and that's epidemiology. So this is all about building mathematical
Andy, sorry,
models.
can I?
Yeah, sure. Is everything okay? Yeah. Shall I carry on?
I think you have YouTube opened and we can hear. No, that's fine. Go on.
Okay.
We're all good. Sorry.
Andy, close YouTube. Okay.
Yeah, that's all right. That's all right. You're good.
Am I okay? Am I okay to continue? All right.
I can hear you, so I think everybody else can.
Okay. All right. All right. Okay. Am I still sharing my screen, everyone?
Yes.
Yeah, still sharing the screen.
Yeah, I don't have the green bit anymore. Is that a problem? So I'll stop sharing and then share again, just to sort of belt and braces. There we go. Let's try that. Okay, there we go. Oh well, is that working now?
Yes.
Yeah.
Yeah, it looks fine.
Right. Okay. So what we're going to look at is the epidemiology of Eyam. So Eyam is let's go and find this little village. So if you've ever been to Sheffield, where myself and Mr. Hughes went a couple of weeks ago, it's in the middle of England and a place called the Peak District. And where this little sort of red marker is the tiny village of Eyam, E-Y-A-M. Now in 1665, a really bad thing happened. So the plague, which has been devastating London, a bit about roughly where Mr. Mompesson's nose is here, got to Eyam. And you have to think about, in those days, for about 300 years, the Black Death had been ravaging Europe. And some calculations estimate that about half of Europe's population died because of the Black Death. Nobody, of course, knew what it was about in those days. These days, we now know it's the Yersinia pestis bacteria. So that's what it looks like. It's quite friendly, doesn't it? But it definitely isn't. You can get a friendly version, by the way, from giantmicrobes.com, which produces cuddly versions of various bacteria. So I've got the common cold, and you can get other things. Ebola is particularly nasty. And so that's what we look at now under a microscope. And the plague bacterium, so it's not a virus, it's a bacterium, would be typically stored in a blood meal that a flea may have feasted upon. So that's how the bacteria can survive inside a flea. There are other ways, other vectors for transmitting disease, but that's probably the popular one of the time. So what happened? Well, probably this flea had got this Yersinia pestis bacteria in its blood, inside its stomachs, etc. And that would have ended up in, say, a cloth, some damp cloth. That's how the story goes. And poor old George Vickers, who the tailor's apprentice, thought he was doing the right thing and was taking the cloth and putting it by the fire to dry it out from the long journey from London. And the fleas were released. And then, unfortunately, the fleas bite quite a lot of the people in Eyam, and about half the population dies. It's a horrible, horrible story. There's a sort of human, amazing sort of tale of heroism, because in the village of Eyam, this guy, William Mobson, who's the new rector, you can tell that from what he's wearing, he decided to quarantine the village. So although lots of people were dying, he realized that if he quarantined the village, then the disease wouldn't spread to the nearby towns, which had much bigger populations. So because of his actions and the heroism of the people of Eyam, they saved probably thousands of lives. Now, why are we talking about this story? I mean, it's an interesting story and links to the sort of COVID-19 pandemic. But what we're interested in is how we can build mathematical models and give that as inspiration to use spreadsheets and Python, etc., creatively. And so how might we go about that? Well, turns out William Mompesson was quite an educated man. And although he didn't understand, he wouldn't have understood the plague itself, he did understand quarantine because of quantagioni, which is 40 days from the Venetians. So they knew that people were, on a sort of the merchants were on this little island for 40 days and they survived. It's likely that they didn't have the Black Death. So he quarantined the whole village, and food would be passed, by sort of left at this special stone. I think you can see that to the day if you go there. But what he also did is write down the number of people who were infected. We call this the infectives. The number of people who might be infected, so everybody else that doesn't have it, and a log of the people who had died. I don't think anybody recovered during that time, unfortunately. But obviously, with modern medicine, COVID-19, the recovered population was much, much higher than this one. So what we're looking at is a really simple model where you start off with susceptibles, all right, and then if you get the plague, you become an infective, and then unfortunately, the chances are after a certain amount of time, you will die. So we have three possible labels to the population: S, I, or D. Okay, and if you actually Google epidemiology or pick up a book, you will talk about SIR models. So R is the sort of removed population. I'm going to call that the recovered because that sounds more positive. So I'll distinguish the R and the D. So an SIRD model is essentially what we're doing. And you can think about this in terms of sort of buckets of liquid. You do this in practice, and my collaborator, Dr. John Cullen from Winchester College, we wrote a paper a few years ago in physics education, which describes this model. And he actually built a water-based system to model it. But we're going to be looking at more in terms of spreadsheets and that kind of thing. So Montesson recorded a table of these things, and you can plot that. So this is our kind of starting position. So this is actually Montesson's data, albeit sort of averaged over a few days. So this is the sort of 4-month timescale to this sort of one of the waves of plague hitting Eyam. There were several for that, sadly. And what can we see? Well, the infectives rise to a peak of about sort of 25, 26 people and then drop. The dead rises and then tails off, and it becomes a sort of plateau. And the susceptibles drop the steep gradient, and the gradient diminishes. And that is, in fact, is quite characteristic of how a lot of epidemics work. And towards the end of today's session, we'll have a look at some of the data from COVID-19 and how we might make some sense of that. So essentially, this is our question. Can we develop a mathematical model to predict what these curves are? All right. And indeed, does that tell us things which are more general than the plague at Eyam? All right. Can we model things like Ebola in Liberia? Or maybe could we say something sort of about COVID and other things? All right. So, and in fact, the full story of this pretty much delves into all of A-level further maths. Okay, so we're not going to do A-level further maths in one session today, but if you really want the full story, you can have a look at this. And in fact, if I can do a shameless plug, it's in Science by Simulation, my new book, which is out now. So I'll show you how to get hold of that if you're interested at the end of this lecture. All right, so we're going to develop lots of techniques to solve this. All right, so you can imagine this is a case study, an incentive for you to do some computer programming and mathematical modeling. Right, so I'm just going to check in there anything in the Q&A. Not yet. Right, so let's have a look. So there we are. There's a bit of a summary. There's me. When I went to Eyam, it was the middle of COVID. Nobody was there, so it's a bit of an irony, really. And there is the blood meal. And there's a few nasty pictures coming up. So if you just had your dinner, you might want to close your eyes. So there we are. That's not too bad, actually. That's what it looks like under electron microscope. Yersinia pestis, all right, which is discovered by Alexander Yersin, I think. This is Guy. Here we are. In about 1900, something like that. And there we go. So that's a nice healthy flea, and this is an unhealthy flea. All right. Okay, so a little bit on plague. We're really going to be looking at this idea of fleas transmitting it to humans. And it was a bubonic plague. So unfortunately, getting plague is a really nasty thing. So you get these sort of lymph nodes which grow. And so there's some tales of woe. Thankfully, this isn't real. So this is a bit of a nasty picture. Sorry about that. So these are the sort of people who dress up as zombies at the weekend and wander around. This guy has got something that looks a bit like a bubo. And this is what might have actually happened. So it will go everywhere. Look at those fingers, it's horrible. So very, very nasty. And actually, this is a real picture. So plague is still around, sadly, in the world, but thankfully we have antibiotics. So antibiotics are something we need to protect, and we need to develop new ones. So, we wouldn't want to revisit the problems of the 1600s and earlier. But that's actually what a BPhO looks like. It's pretty horrible, isn't it? Okay, so now some maths. So this is a table of Mobson's data, and I've got S, I, and D, the susceptibles, the infected, the effectives, and the dead. And I'll explain a bit why we've taken the logarithm of those things and what this means. Okay, so there we are. There we can plot it. That's William Mobson. Okay, so what we're going to do is look at something called the Eyam equations. So if you're kind of new to this kind of idea, what we're trying to achieve is what is the smooth curve which underlies this data, all right? How can we do that? Well, that's quite a hard ask, how many curves do we know that have a peak to it? Well, that could be loads, quadratics, cubics, all sorts of things. Normal shaped curves, e to the minus x squared, could be anything. Whereas what is more interesting, perhaps, is to work out the slope of the curve. And of course, we do that all the time in physics. So before I go to the next slide, can you give me an equation of physics which we define in terms of a slope or a gradient? Okay, I'll give you 20 seconds to put something in the chat. But can you give me an equation which involves a gradient, something that's dependent with time? Okay, so a change in y over change in x, that is a gradient. Can we get a physics equation, do you think, that involves a gradient? Okay, yeah, loads, brilliant. So acceleration, the rate of change of velocity. Yeah, so Newton's second law, mass times acceleration is vector sum of force. All right, so we define mechanics, motion, in terms of a rate of change of velocity, which itself is a rate of change of displacement. All right, so if we can add up the forces on an object, we can work out its acceleration, and hence we can work out its velocity, and hence we can work out its displacement. All right, that's our recipe for mechanics, or much of mechanics. All right. Okay, so these are the equations for Eyam. Check out, I've got my So there are 4 of them basically, but really there are 3. So the first thing we have is how the rate of change of the recovered and dead depend on the number of infectives. So in Eyam, we can take R to be 0. Let's assume nobody survives. So this is a bit like exponential decay, except it's the opposite. So the rate of change of the dead is proportional to the number of infectives. So if we double the number of infectives, we double the rate of which our dead increases. Okay. All right. And just ask a quick question: how much mathematical knowledge is needed for this? So I'm not really going to assume much at all. Okay. If you've done a little bit of calculus, you'll spot the notation. But we'll build this all up. All right. Let's hope that's okay. If you want to see more, then you can delve into the presentations and the books, etc. And if you fancy getting a MATLAB free trial, that's awesome. But we'll do some things with Excel a bit later. All right. So the first equation is the rate of change of the dead is proportional to the infectives. And our constant of proportionality is something that we want to try and find out. Okay, what else have we got? The rate of change of the susceptibles. Now, that's also going to be proportional to the number of infectives. If we have more people who have the pestilence, the rate of change of our susceptibles will increase. And the simplest model we could think of is maybe have that as direct proportion. So ds by dt, so a little bit of a change. So if you imagine dt to be a very small amount of time, all right, then ds by dt will be the gradients of the graph of s versus t. And so that would be proportional to I in our first model. But it's also got to be proportional to S as well. Because if you think about it, if we had 500 people rather than 250, that proportion would double. Well, the proportion would be the same, the numbers would double. So we've got an interesting problem here. So ds by dt is proportional to S and I. Oh gosh. Now, that's the kind of maths you won't see in an A-level course. This is what we call a non-linear differential equation. All right, so how on earth do we solve that? All right, more about that later. And it's got to be negative because, of course, that's going down. What else do we know? Well, in the village of Eyam, we're assuming, so I've got a picture of Eyam. There we go. So in this, actually, I'll go back to there. So in the village of Eyam, we're assuming there's not enough time for reproduction. It's pretty bad time. Everyone's got the plague. So assuming the population, S plus I plus D plus R, though R is 0 in our case, is a constant. All right, so we can't there's no one coming into the village. There's no one coming out apart from, when they died. So we're going to assume that this is a closed system. All right, so things like, lots of closed systems, we think sort of like in charge when we're doing circuits and all that kind of stuff, or conservation of energy. So this is a closed system of people, and you can't be S and I. You can either be susceptible, infected, or dead. All right, so there we go. Those are our three equations. And if we find the gradients of all of those things, so ds by dt plus di by dt plus dd by dt, we get 0. So that means we can write a third equation involving the rate of change of the infectives. And this is quite interesting, because basically what this is, it's the change from the susceptibles. All right, so you can imagine like a flow of people, or flow of liquids or something like that going into this I box. And then we've got flow out of that box going to the Ds. All right, so there we go. So we've got the rate of change of susceptibles making this bigger, and the rate of change of the dead making this smaller. So that difference is given by this. So we have, this is our dynamics, if you like. All right, this is our Newton's second law for D, S, and I. Okay. So there we are, and then if we're doing sort of mathematics, we call these differential equations. All right. Okay, so there we are. So what is the simplest model that describes the key features of Mompesson's data? All right, let's have a look at this one. So there we go. Let's just sort of summarize what we've just done. So we've got our rate of change of the dead, we've got our rate of change of the susceptibles, and if our fixed population, all right, so I plus S plus D, let's assume that's what we know at the start of the model. So at Mompesson's data, we can work out that number and that number. All right, that kicks things off. That's I naught and S naught. All right, let's just say we know that, and we can differentiate or find the gradient to find this lot here. So those are our Eyam equations. This is our model. So that's basically the mathematical input to this. The question is now, how do we solve it? Okay, so okay, right. So just a couple of a little bit more. I'm just going to push this ever so slightly. So the little bit in the italics for those who've done a bit of further maths, a bit of calculus, you can indulge in this one. But let's just explore this equation in a slightly different way. So if I factorize out I from this, I've got beta s minus alpha times I is di by dt. So you can kind of see two regions for this. How do we make that positive or negative? Well, it's going to depend on the sign of the thing in the brackets, because I can't be negative. We can't have a negative number of people who have got the pestilence. That's got to be positive. So if beta s minus alpha is positive, which means s is bigger than alpha over beta, then our epidemic's going to grow. If that thing in the brackets is less than 0, all right, which means s is less than this alpha over a beta value, then our epidemic shrinks. So that defines where we are on that curve. So whether we are above, so that point there, all right, that's when our bracket is 0. Okay, this one is our bracket's going to be positive. That's our bracket's going to be negative. All right. So there we go. And so we have this threshold of susceptibles where our epidemic will grow or diminish. And in fact, that's really interesting, because if you don't have enough people, then your epidemic just will decay exponentially. Whereas if you have enough people, it will grow to a peak and then decay. All right, and that's a common property of epidemics. And if you, perhaps the text is a bit small to read, but basically what you can do is you can differentiate this twice if you've done the calculus for it, and you can find d2i by dt squared, like the acceleration of I, if you like, and that you can show that's actually less than 0 when s is equal to alpha over beta. So that means that it's a maxima. But that's all great. We kind of knew that anyway, because by plotting it, we know that the infectives go up and then down. It doesn't sort of have a dip and then rise. Okay, so that's a bit of calculus. Right, let's solve it. So if you're really new to calculus, or even if you're not, very quickly in the chat, if I gave you, say, an equation like dy by dx is x squared, what process would you do to find y? Oh, that was quick. Integrate, excellent, fantastic. We do need to know the initial conditions. So I'd have to specify, you know, y is 0 when x is 0, something like that. Now, how do we integrate a horror like this? We can't even rearrange it. So actually, we can do any differential equation by numerical method. So now, obviously, if we can integrate something, all right, then that's wonderful. But many equations we can't. But we do have an incentive for solving them. So we're going to use this guy's method. This is Leonhard Euler. All right, that's how you pronounce Euler, from the great Swiss mathematician. So what we're doing is we're assuming these are our Eyam equations. And what we're going to do is we're going to make time, rather than being infinitesimally small, we're going to make our time a finite but tiny amount. So let's say in our case, maybe about 0.01 of a month, something like that. We're going to call that delta t. And then what we'll say is that these equations we're going to approximate. So in time delta t, right, what is the change in s? Well, it's going to be minus beta si times delta t. So we're looking at these derivatives and we're going to say, well, if we were to sort of zoom into our graph, let's assume they are actually fractions. So this is what we produce, and we can then turn these equations into an iteration. All right, so we start off at time 0, and this is from Mompson's data. So S naught is 235, I naught is 14.5, and D naught is 0. Now, I'm going to leave it a little bit mysterious. In a moment, I will show you how I've worked out alpha and beta. Okay, so the challenge from today, if you really want to be awesome, is to see if we can follow this process and actually work those numbers out for yourself. But for the moment, I'm just going to tell you what they are. All right, so we're going to have our time iterating in a loop. So this is now the sort of stuff that we do with computer programs. All right, so we'll do in Excel shortly. But if you're using Python, that'd be great. If you've got MATLAB, that's awesome too. But you know, any other language would work. In the challenge last year, I think almost everybody used a slightly different language. That's fine, because to present your computational challenge, it's not a paper. You have to produce a 2-minute YouTube video telling us about your solution. All right, so you know, you bring up the code. This is how I did it, etc. All right, and you can do it in pairs too. So we'll give you about 2 or 3 months to achieve this. I think the deadline is going to be something like in August, something like that. So how do we do it? So here's our first iteration. This is how we work out the next time value, just by adding delta t's. And then how do we change s, I, and d? Well, what we do is, so we just use our equations here. So we subtract beta si delta t from the previous one. This one, we add beta si minus alpha I delta t, and the n stands for the index of the iteration. So n go from 1 to 2 to 3, etc. So a couple of questions. Okay, yeah, we're going to do a bit of coding. Absolutely. Alpha and beta. Well, if you think about it, all right, you can look at what they might mean from the equation here. So if you think about what's the units of the left-hand side. Put that into the chat. What's the units of the left-hand side of this equation? Yes, people times the -1. So yeah, so we'll have the people of population is just a number, so it's times the -1. So that must also have seconds to the -1. So in fact, 1 over alpha gives us a time scale. All right, so 1 over alpha might be something like how long it is on average when you get the disease to when you go from I to D. You know that, and that's quite an important number. All right, so the bigger alpha is, all right, then you know the smaller the time it is. So if alpha was a large number, this is not a very nice virus. It's like some sort of neurotoxin. But of course, that's not going to spread very easily because everyone just dies instantly. Beta is more kind of the virulence. All right. So how does it sort of spread? The bigger the beta, that gives you a sense of how the disease spreads. All right. So, okay, so these two numbers will characterize our epidemic. Right, let's do some things. So this is how I would do it in code. But I think what we'll do is we'll do it in a spreadsheet first, I think. So I'm just going to come out of this. Now, if you've been diligently clicking on the links, you can find a little spreadsheet. So if you download the file, there we go, you'll get these directories. So if you look at the Excel and Python Eyam model, all right, and we click on this little spreadsheet here, All right, so I'm going to give you a flavour. I think we probably haven't got time to sort of build it from scratch today, but you know, I recommend if you want to do one thing after today practically is have a go at building a spreadsheet. So let's just sort of zoom in and see how it works. All right, so I've got a graph here, which the curves you've seen before, with Mompesson's data. The actual data comes from this separate tab. So I've plotted it, and I've just sort of plotted the data on this graph, referring to the data here. Okay. So that's my initial population. So these are my inputs to my model. All right, the initial number of susceptibles, infectives. 14.5 might sound a bit weird. That's just a sort of average over 2 weeks rather than actually half a person. All right, and then we've got beta. It turns out beta is best to be think of as alpha over 163.3. I'll show you where that comes from soon. And that's our time. So I think I've used 0.1 of a month rather than 0.01. So these are our starting conditions. And then what I do, if I click on one of these, so maybe I can make, I can zoom in here. Can someone tell me, is that a bit too small to read what's in the box at the top?
No, it's fine. Well,
okay.
Well, as long as you're not using a phone.
So let's just have a look what that says. So it says equals C14. So C14 is the cell above it. So that's in this case, the starting number of susceptibles. So I've got my starting number of susceptibles, and I'm going to add $F11. So $F11 is my time step. I can actually give that a name actually in Excel. I won't do that now, but you can make it look a bit more like an equation. So there's my time step, delta t, and there is my change in S. So I've got minus beta, which is $F11. Now, why have I got the dollars? Well, in Excel, that means it doesn't increment as we scroll down. So I'll show you how those numbers have changed. So if you want to get a constant, you can use dollars, or you can actually give it a name. Okay, and then inside my bracket, I've got D14, which is the I, and C14, which is S. So I've got minus beta SI times delta T plus the previous S. So that is exactly what I've got here. I think these are slightly larger in this slide. Okay, so what I've got, I've replicated that iteration in Excel. And I'm doing exactly the same thing for I. So there we go, that's the previous I plus delta T plus this lot. Okay, and then the D1, that's a bit easier. So the previous D plus alpha plus F9, which is going to be so that's the alpha constant, that's delta T, and D14 is the previous I. So all those equations I can represent in terms of the previous cell. So if I just get rid of maybe these ones, and I can show you how it replicates. So hopefully it works. So there we go, just the Mompesson data at the moment. And then what I'll do, if I drag these down, and you can click in the little square at the bottom if you wish, I'll drag them down. We now start to create our curves. There we go. And essentially what we've done is solved a differential equation of our choice. And there we are. So if we go down this column, you'll notice that the numbers will change just increment by 1. That's what dragging things down in Excel does. So I think, how long have I got? Actually, we better sort of move on. So there we go. So give that a go. I think, give yourself an hour. If you've never done Excel before, you might want to look at some tutorials. If you're really a real whiz with Excel, you'll do that really quickly. And in principle, you can solve any differential equation you like. Okay. So there we are. So those equations here are exactly in Excel speak what we've got in this presentation. All right. So we're assuming that delta T is a fixed amount, and we're finding the change in S is minus beta SI times the change in time. And we're adding that to the previous one. Okay. So if we want to do that in code, so this is MATLAB code. So it's a bit cleaner, you might see. So I've got a function which works out T, I, S, and D. I'm initializing a vector of outputs. So I think we've got, this works out all the times, however many those are. And then I've got a vector of however many elements. That's initially initially all the same numbers. And then I loop through. So this is a for loop. And I basically implement this in MATLAB speak. So different languages, you might have a bracket, a square bracket rather than a curly bracket. Okay, so there we are. All right. So this is how we work all these through. So we're representing these equations in a loop. And in fact, let's just sort of talk about how we get the alpha and beta, and then I'll show you how we've implemented that in different aspects. So a little bit more calculus is required here, because it turns out you can actually go a bit further than just using the numerical method. Because when I was looking at the data, I was thinking, well, can you find alpha and beta from Maupassant's data directly? It turns out you can. So what we do is we can follow the steps here. These are my two Eyam equations for S and I. And if we divide them, we can get rid of the time dependence. And with a little bit of cancellation, we end up with an integral of 1 over S and 1. Okay, and I'm sure a lot of you will have met this in maths, that the integral of 1 over S gives you the natural logarithm of S. Okay, and we've got this constant in front of it. And so if you sort of expand that out, what you end up with is something that looks like this. So the logarithm of the initial susceptibles over the susceptibles at time t multiplied by alpha over beta is the population at the start minus I and S, which are the infectives and the susceptibles at time t. So remember, what is alpha, what is beta? Alpha and beta are what characterize our Eyam equations. So if alpha was large, that means it's not a lot of time for you, if you've got the disease, for you to die. If beta was really large, then the disease is going to spread very quickly through the population. Now, if you look carefully at this, if we call that y and we call that thing x, we've got y is alpha over beta x. So this is like physics, yeah? This is like the lab. We can basically do a y equals x, a line of best fit from our data. We have to compute these things, and the gradient of that graph will give us alpha over beta. So there we go. That is it. So this is another challenge. So if you've mastered the spreadsheet, all right, now you can try and do a line of best fit of plotting this lot versus this lot. And you'll find the line of best fit gives you a gradient of about 163. So that's what alpha over beta is. But what is alpha? So this is where you do need to use some code. You can't really do this very easily in Excel. What I've done, so this is the best fit function, skip over that. So what I did is I ran the whole thing in a loop with a variation of what alpha is. Okay, so you end up, so the thing we showed you before, so this is a function in MATLAB which works out our curves using our Euler method in a loop, but we have to give it alpha and beta, and in fact the maximum amount of time and the initial value. So these are the inputs to the program. And so if we run that through, we can compare our estimates of S, I, and D to the actual model. So that's the model ones, and that's actually what they are. And there's a little subtlety here that we have to work those out at the times of the Maupassant data. It requires something called interpolation. Okay, so if you do that and you add the sum of the squares, we get a number. And what we want to do is make that sum of square differences as small as possible. So I ran this for, I think, about 100 different values. And the bottom of my curve, the smallest value of my sum of square differences, gives me my optimum alpha parameter. So I know what the best alpha is. I know what alpha over beta is, 163. Now I can compute the result. And there we go. That's the best fit. So let's explore how that was done. So I'm going to kind of come out of here for the moment. And so we used our spreadsheet, but that's assuming we know what beta is and alpha is. So that's not so helpful. That's sort of that, you know, that's as soon as we know the answer. So I'm just going to move that. So here is a model I did in Python. So if I open that with idle, okay. So Python is free. Is that readable? Okay.
Yes, it is perfectly readable.
Excellent. Yep. All right. Okay. So there we go. So this is what Python looks like if you've never seen Python. The hashtags mean commentary. So when you're writing computer code, the best tip I can give is start with a commentary. So these things here, this is what I'm doing. All right. And I would literally work it out. So I'm going to define a range of alphas. I'm going to find my maximum time, my time step, maybe something about the plots, how big they're going to be. and then I'm going to work out my solver, my loop. So if I didn't know the notation for doing this, and let's say you've never coded before, I'd start off with my comments, and I'd literally write out in English or whatever language you want to use, what it's going to do. So there we are. So I'm going to initialize my output vectors of time, infectives, susceptibles, and the dead, and I'm going to loop through to work everything out. All right, and hopefully you can see that looks a bit similar to what we said before. The difference is Python uses square brackets for its indexes of arrays, which are the same thing as a vector. All right, every language has its own quirks. And then we use the return function to give you the outputs, and def means function. So it's pretty identical to MATLAB. And then so we define various things. There's a function of the best fits, etc. And then what I do is I run through my model. And I don't know if you can sort of see this here, but this is my loop. So what I'm doing is I'm running through a whole range of alpha parameters. And what I'm doing is I'm going to say which iteration number it is to the command window. And then I'm going to store my sum of square differences and then plot them. And once I've gone all the way around that loop, I can then plot a graph and then plot the final graph. So you need to go through this step by step. And you can access this code from that link. So not too many lines of code here. Let's go and run it, shall we? So if we double click on this, we get our Python window. There we go, a bit of feedback saying it's running. There's all the iterations. It's computing the model, and then it's done. There we go. So it's always a good idea to give your program some feedback so you know it's actually doing things. And if I press return, so it's made me, using matplotlib, some graphs. So there we go. So this is, actually it's probably there we are. There's my sort of final results. So look at those nice curves. And it's worked out that alpha is 2.894 and beta is 0.018. So how did it do that? Well, there's my line of best fit. All right, I0 plus S0 minus I minus S versus the log of S0 over S. So if you plot that to the line of best fit, that gives you 163. I had to work that out. I have to code that up myself in Python, but there are libraries you can acquire so that you can do it by yourself in Excel. So this is Mompson's original data. And this is the thing that we need Python for. We can't do that easily in Excel. This is plotting the sum of the square differences between I, S, and D interpolated at Mompson's times. Okay, and the minimum of that curve gives us our best alpha. There we go. So that's basically it, and that solved our Eyam problem. So how else might we want to visualize this kind of thing? So what we've got is we can also make an app. I've done this in MATLAB, but you can use other things as well. So here is the Eyam MATLAB stuff. So there we are. This is an app I made in MATLAB. And what you can do, there's the Mompson data, and we can generate a model with the inputs defined here. We can change these sliders. So for example, if I make the infectives a bit higher, right, we'll change the curves completely. Let's just reset that is there a reset button here? I think I have to redo it. There we go. There we are. So that's the original data. If I change alpha and alpha beta, I can also change these curves. So if I make that bigger, so there we go. I'm making alpha larger. So what you find is, that will sort of the transition from the infectives to the dead will happen much, much quicker. If I increase this one, all right, I can also change the curves. All right, so you can have a whole family of curves which you can produce by changing these. And you can kind of move these around, okay? And you can explore what happens if you modify these parameters. So there we go. That's something you can do, and quite a few of our students did those apps. So if I go back to the presentation, here's one I made earlier. And this was done in some sort of game engine development environment by a student from Barton Peveril School called Alfie Baxter. So there's loads of ways you can do this. You can do it on a smartphone. That'd be quite interesting. If anyone fancies doing that for next week, I'd be very impressed. Okay, so right. So we have, I think, about 10 minutes. Is that okay? So I will just make a slight sort of nod to a few other projects where we've extended this. Before I do that, though, let's just see if we've got some questions in the Q&A. Has anything not been? Okay, so
we've had quite a few questions about how people can use Python and which version they need and all of that. So I was thinking maybe for next week we can sort of make a list of instructions rather than addressing that now.
Yeah, I think so. So I think what I would recommend is download all the code. I think there's only one Python program in it, which is the one I just showed you, but you can get that immediately. So Python 3, python.org. So I'll put this in the chat actually. So if I go to the Eclecticon, I'll just make that slightly smaller. Right, so if I go to programming, I'll stick this in the chat. There is a course in coding, and if you click on the Python Raspberry Pi bit, there's all sorts of help. So I'll stick that link in, is that in the chat? Okay, hopefully you can get hold of that. And while I'm here, I'll also put the link to Science by Simulation as well. So the first chapter of this is all about literally everything that you might want to know about this model. So there we go. That is the and you can get sort of there's a page. So each of these is a link to the description of the book chapter. There are YouTube sort of tutorials as well, and MATLAB code you can download. So the Eyam stuff is pretty much what we've just been talking about. Okay, so we had Alpha did this little this little app. So I'm going to skip around a bit. So it turns out you can actually. I think I'll leave the bit about Ebola. I mean, basically, we applied this technique to Ebola. Which is probably the right graph I can use. Probably. Let's have a look. Yeah, so here we go. So Ebola is a pretty horrible disease. That's what it looks like. And that's Sierra Leone. So in 2014, there was an outbreak of Ebola there. Now, what was interesting is that the World Health Organization, we didn't know the susceptibles. All right. We didn't know how many people have died. What they had was the sort of confirmed infectives. So that's a slightly different setup that we had for Eyam, where we know everything. So a much harder problem. So we did a slightly different model, but it's essentially the same kind of system where we're trying to find a fit to the infectives versus time curve, which is what we've got here. What that produces is something called the R0 number, the basic reproduction number, which if you were following what was going on with COVID, was a very important thing that was discussed every week. So it's about 1.85 for Ebola, and what we actually worked out from this very crude model is actually quite close to what sort of professional epidemiologists apparently did. So we were quite pleased. But also we can figure out from this what the population N that produced this set of data, and indeed the susceptibles. So you can actually work everything out, and we made a lab for that. So the numbers here, it's not quite alpha and beta. There's another parameter called eta, which goes between 0 and 1, which is how you solve this. But that's a story for another day, I think. Okay, so I think I'm going to leave you with this. So this is really where you would want to go with this kind of model, because everything we've done so far is deterministic. All right, it means that we start off with Mompesson's data. We always get the same curve. And that's not really how things are. There's a lot of random chance involved. So how can we involve probability and chance? How can we develop our models? Okay, so this is called a stochastic process involving some randomness. And what we were trying to work out is a probability map of susceptibles versus time. What the colors mean. So for example, I'll take 2 months here. All right, the color gives you an idea of the greater chance of my susceptibles being a certain number. So there's no way, absolutely impossible, that we get 20 susceptibles at 2 months or 250, because there's just not enough of them. All right, the greatest chance is when they're about 110. Okay, and you've got a similar graph for infectives versus time. So this sort of heat map will tell you where the greatest chance is of a given infective at a certain time. And what you can see is it kind of tracks the deterministic model that we've just created for our, what we've just been doing for the last half an hour. All right. But what are these other traces? How do we work those out? So this is how we do it. So this is called the Poisson distribution. Just as a sort of kind of show of hands, can you sort of like raise your hands if you've heard of the Poisson distribution before?
Sorry, I'm just going to let people raise their hand. 2 seconds.
Yes. Excellent. Lots of hand raised. Very good. So I think we've got about 10% of you, maybe more. Okay. All right. So the Poisson distribution is all about when you've got, so think about football. So when you've got, well, you might know about the binomial distribution where you can either, so if you're in a football situation, you go and kick a ball and it either goes in the goal or it doesn't. And that sounds like a very random game of football. It sounds like the football team that I used to coach when I joined Winchester College, you know. And so basically in football, the chances of scoring a goal from any given kick is pretty low, but we have a lot of kicks. So over a game with many, many kicks, you would have thought there's a reasonable number of goals that would be scored. So this is what it is. The Poisson distribution is a limit of a binomial distribution, which is you either do something or you don't, you score a goal or you don't. With a very large number of trials, each one has a small probability. So this is a well-known there's a formula for it, for working out probabilities. So what we're assuming in any given time step, all right, we're assuming a Poisson distribution for what happens next. All right, because Poisson distributions involve one parameter, the mean number of goals per game, for example. And then from that, you can work out, in fact, there's a picture of it here. All right, so it's a very, very good game, 7.4 goals per game. That's probably not a World Cup game. So it will work out sort of what's the probability of 0 or 1 or 2 or 3 or 4. It's a discrete distribution, all right? And, you know, if you add those all up, you get 1, okay? So the mean, that one there, the number of goals per game, defines the shape of this curve. And what we're assuming is that also works for our change in I or S between our time steps. So if you look carefully, that thing there is going to be the change in our susceptibles in a time step. That's what we used before. We're going to call that X, well, minus, yeah. So X is that, the delta S is minus X in a time step. But of course, that is the mean, all right? So let's just say that was, I don't know, a change of 1.23 was what we worked that to be in a given time step. So the number of people that would actually change would be 0 or 1 or 2 or 3 or 4 or 5, 6. Okay, it would be more likely to be about 2, because we can't have, you know, a fraction of a person in delta t. All right, we've got to have a whole number. So this is why we need this random model to make it realistic. So we can define another Poisson variable, which is the number of people who go from the infected population to the dead population. And we know that changes alpha I delta t. All right, so again, we can stick it in the Poisson distribution as a mean and then work out that number. So that means the number of people, the change, if you like, of the infectives and the dead. And the change in the infectives is the ones that come from the susceptibles, that one, and from the infect and go to the dead, that one. All right. So if we put that together, all right, there's the Poisson distribution, by the way. And I'll gloss over how we actually work out these probabilities. But this is what the MATLAB code would be. Whoops. So we're working out, it looks very similar to before, but now we actually work out our probabilities. And sampling from the Poisson distribution is the key to this. So that's something to read up. Okay, I don't think we've got time to look at today, but it's described in this slide. So, okay, so what do we produce? Well, we get this. And in fact, I think what I'll do is I'll actually run it live before we close down today. So here's MATLAB, and we've got the Eyam stochastic model. And if I just open that up, and I think I've set it to be 42 iterations, because obviously 42 is the answer, okay? So Hitchhiker's Guide to the Galaxy, there we are. So I'm doing 42 iterations. This is 42 possible I, S, and D trajectories. And there we go. That's what it looks like. So if we open that outside MATLAB, you can see we've got a kind of density here. And then there's lots of epidemics which just don't have the right number of susceptibles, so they die out. Whereas some of them, actually, I increases, okay? So this is really important, and we're probably kind of coming to a close now. So I think I can show you one slide about COVID-19. So there we go, there's COVID-19. And let's find, I think this one probably, there we go. So COVID-19 was obviously a massive tragedy. But from a data perspective, the data that's collected is really useful for the future. And I'd recommend all of you having a look at the Oxford World in Data data set. Although you can use, I've downloaded the data for you. You can get that yourself. So this is a horrible graph. This is the graph of the number of people who've died over. Can you hear my voice? Actually, is that still okay?
Yeah.
Okay. So this is a graph of the cumulative number of people who died in the UK due to COVID-19. And again, there's a lot of variability there, but in the UK, you have to have a death certificate. So we can argue that's probably the best data we've got. Now, during COVID-19, we couldn't basically test everybody, and that would have been impossible. So the question is, how many people had it? How would you know? Now, this is a really difficult question, by the way, and I'm not saying this is the answer. Big caveats here. But if we use the Eyam equations, then we know that the rate of change of the dead is proportional to the number of people who we think have got it. So we can kind of reverse engineer that. If we know what the curve of the D is, we can find the gradient of it numerically. This is how you do it. All right, just the change over a D over the change in time. And if we know we can estimate what the constant is in front, then we can actually estimate what the infective curve is from this. All right, so I've differentiated this, all right, to go from there to there. Now, this is where, you've got to do a little bit of wet finger ideas. So I looked up on, so I think it was the WHO website or a medical website, and around about, call it 1 in 10 days, 9.3 days is the time between getting COVID and something bad happening, either recovery or death. This one, K, is what we call the mortality fraction. So thankfully, for COVID-19, most people made a full recovery. But at the time when I wrote this, it's thought that certain groups might have like a 1% chance of, unfortunately, dying. So rather than, I have to sort of scale this to get I by this fraction here. So if you do that, then my estimates are, in the first wave, you get just above 800,000 people in the UK had it, and it rose in the second wave. Okay, so these are not the same curves that we saw before. Remember, we had lockdowns and all sorts of things, but it does give you an idea that if you think this equation has some merit, then you can go from what was published to what we probably wanted to know. And I don't know the full answer to this. You'd have to look into the data that was published by Imperial College who are modeling this, but this is the kind of curve that I think people were interested in, actually how many people were infected at any given time. And you can estimate that from the cumulative graph of the dead. So that's a bit of a grim story, but hopefully it will sort of give you some insight into how we can build these sort of simple mathematical models, how we can use spreadsheets, how we can use some basic coding to really get an idea of what's going on, and certainly to ask the right questions, from what the government's telling us to do. So there we are. My recommendation for next week, challenge number 1 would be to see if you can build an Eyam spreadsheet. So if I can find one, it's something I'll come out of this rather than, let's go for, where's my slide? There we go. So there we go. So challenge number 1, could you build one of these? All right, using all the numbers that we've got. All right. Challenge number 2, could you use line of best fit to find alpha over beta, which was this one. Okay. Challenge number 3, could you put that into a loop?
Just with the previous slide, we had a couple of questions on why is the best alpha value a minimum and the sum of squared model. I don't know if you have a chance just to
sure. So that would be the ultimate. Well, the ultimate challenge is to build a stochastic model. But I think you probably want to have might be more of a project if you're coming to this fresh. So just so one. I think we'll answer the last question. So what this means, let's see if we can refer it to. So there we go. So what we've got. This is every time we have an alpha and beta value. Let's say we know what alpha over beta is. That's a 163. So let's guess a value of alpha. We've got a curve of the infectors. We've got a red curve. Okay, but it might not be the one. We might not have the right alpha value that cuts through the data points. We'll also have a blue curve, a D curve, and a green curve. And what we can do is we can work out the difference between our data and our curve. So if I hover over, say, the susceptibles, So the model susceptible minus the well, the difference between those is that distance you can see there on the graph. All right, it's not very much because this is the best fit. But if alpha was a bad one, that would be a bigger number. Now we square it so we don't have any problems with negatives, and we add up the difference from this and this one and this one. So that's what we're plotting here, the sum of those squared differences between our model and our data. But the technicality here is you have to evaluate your model at the times that Maupassant had the data. And so you have to do something called linear interpolation, or a more fancy term of interpolation to do this. All right, so you might want to look that up in a computer programming language. But that's basically what we're doing. I hope that made some sense. Okay, any more questions? I think we definitely ought to stop now. Any more burning questions? Okay, well, in that case, I think I'll leave. Thank you very much indeed. So I hope you enjoyed that. Was a pleasure to see you all, and do come back next week. I haven't decided what we're going to do yet, so but it will be exciting.
Yes, perhaps we should just say to those attending that you need to keep an eye on the BPhO webpage for the computational sessions. We're not quite sure what we're doing next week, I think, at the moment. So keep an eye on things. Dr. French has actually got a parents' evening, and you know how important those are, discuss progress. So we're just kind of, we were talking earlier about what we might do next week. So keep an eye on the webpage so you know what's going on. We'll try and send out emails as well, just to inform you once we've made a decision. A lot of you were struggling with the maths there, quite rightly too. It is difficult. This is not a maths session. You need it, but then actually just use it. So and somebody else was asking, what's the best way to learn Python? Well, get a little project to do and start developing it. It's not like learning sort of to do algebra in the same way, because there's lots more to it, lots more variation. You have to do one of these little projects. Maybe this one is more mathematical than some of them. And so those who are not familiar with all these differential equations might want to try something simpler, which will be coming along later. But they're all independent ideas. So don't lose heart. You get lots of ideas. You can see what can be done with this and how important plotting the data is. And that's really crucial. So you can do lots of stuff in Excel, and you need to have a go at that. Don't sort of get bogged down in Python if you haven't done any coding before. Get Excel out and try doing simple things. Don't expect that you can kind of develop sort of 10 years experience in 10 minutes. It doesn't work like that. It's a slow process, but you get better by practicing. So thank you very much, Dr. French. And we'll look forward to whatever's coming along in the next few sessions. Right. Lena is going to close this now, and we'll see what we do next week. Thank you very much.